this lesson, we're going to be looking at applications of rational equations. We're going to be translating word problems into rational equations and then solving those equations. When dealing with applications of rational equations, there's three main types of problems that we'll see. The first one is a working together problem, where two or more things work together to complete a task. There are distance problems, where distance is equal to rate times time, and we normally will solve so that time is equal to distance over rate. And then there's a distance problem that involves the wind or the current. The first type of problem we're going to look at is the working together problems. These are the steps that we should follow. We're going to write each person or thing as its own fraction, and the fraction would be the number of jobs over the time. We're going to add the two individuals and set it equal to the together fraction. And then once that's set up, it's just basic solving rational equations, where we're going to find an LCD for all three of the fractions to cancel them out. And then once you have a one-line equation, we're going to solve the equation accordingly. I make sure to double check your answers against the domain restrictions to make sure that we don't have any extraneous solutions. We also want to make sure that the answer we get makes sense in the context of the problem. For instance, we know that time cannot be negative, so if we're solving for time or rate or something where a negative number is not an option, that is an extraneous solution. And then we're going to make sure that we're actually answering the question that they're asking us to answer by plugging in the x value as appropriate. And since these are word problems, we will be including units in our answer. So here's an example. John can rake a lawn and bag the leaves in 5 hours. Sally can rake the same lawn and bag the same leaves in 3 hours. Working together, how long would it take them to rake the lawn and bag the leaves? So what we're going to do is write each person as their own fraction. So first we have John, and the fraction's always going to be the number of jobs over the time. So the number of jobs, even though he's raking a lawn and bagging the leaves, that's one job. He's completing one lawn that he's cleaning up. So we're going to say 1 over, and it takes John 5 hours. So he's 1 over 5. Now Sally, she can rake the same lawn and bag the same leaves, so she's doing that same one job, and it's taking her 3 hours. Working together, how long will it take them to rake the lawn and bag the leaves? Well, together, they're going to complete one job in we don't know how many hours, so 1 over x. So what we're going to do is take John, which is 1 over 5, add Sally, which is 1 over 3. So John plus Sally is going to equal them together. Now that we have this set up as a rational equation, we're going to look for an LCD. So between 5, 3, and x, we know the LCD would be 15x. So we're going to multiply that 15x to the numerator of all these fractions. So 15x times 1/5 would be 15x over 5, which we reduce to 3x. 15x times 1/3 is going to give us 5x. And then 15x times 1 over x is going to just give us 15. So now we can combine our like terms. 8x is equal to 15, and then we can divide by 8. So x is equal to 1.875. We know that our domain restriction here is that x cannot equal 0, which is not our answer, so that's good. Our answer is also positive, and this is going to be in terms of hours, so we know that that is a good answer. And you can always double check your answer by taking that and plugging it into the equation that we came up with and making sure that the left-hand side of the equal sign is equal to the right-hand side of the equal sign. Okay, here's another example. Two pipes are filling a tank. One pipe fills 3 times as fast as the other. With both pipes working, the tank fills in 84 minutes. How long would each pipe take working alone? So again, we're going to set each pipe up as its own fraction. So pipe 1, we're going to call 1 over x. We have pipe 2, and it's so 3 times as fast. So we know that the one that's 3 times as fast will take 3 times shorter. So pipe 2, if we call pipe 2 1 over 3x, that's taking 3 times longer. Okay, so it doesn't really matter which one we call x and which one we call 3x. The idea is that we're solving for 2 different pipes. So we want to make sure that we have 1 as x, and then 3 times as fast means that we're multiplying the first rate by 3. So now together, they take 84 minutes, so one job over 84. right? They're filling a tank. That's the number of jobs. So now we're going to add these together. 1 over x plus 1 over 3x, so pipe 1 plus pipe 2 equals together 1 over 84. So our LCD here would be 84x. So 84x times 1 over x is going to give us 84. 84x times 1 over 3x is going to give us 28. And then 84x times 1 over 84 is going to give us just x. So x is equal to 112. Okay, we know here again that x cannot equal 0 as our only domain restriction. And our answer is not 0, so that's good. It's also positive, which is time that we're solving for. So we know that that is a good answer. Read the question, right? How long would each pipe take? So we want to answer for both pipes. So pipe 1 would take 112 minutes. And then pipe 2 is going to be 3 times that. So it's going to take 336 minutes. And those are our two answers, and we've completed this problem. Okay, so let's look at one more working together. If Carlos does a job in 12 hours, and with the help of Jessica, they can do it together in 5 hours, how long would it take Jessica to do it alone? Okay, so first we're going to set up Carlos. Number of jobs is 1. It takes Carlos 12 hours. Jessica, we don't know how long it takes her, so 1 job in X hours. But we do know that when they are working together, they can complete 1 job in 5 hours. So we're going to set it up. 1 over 12. So Carlos plus Jessica, 1 over X, is equal to them together, which is 1 over 5. Okay, so now again, look for your LCD. In this case, our LCD is going to be 60x. So if I take 60x and I multiply it to 1 over 12, I will get 5x. 60x times 1 over x is going to give us 60. 60x times 1 over 5 is going to give us 12x. So here, if we get our x's on the same side, we can subtract the 5x. So 7x is equal to 60. Divide by 7. And x is equal to 8.57. This is in hours. Okay, again, check our only restriction is x cannot equal 0. This is not 0. It's a positive answer. So this is good. Okay, our second problem that we're going to look at, our second type of problem, is the distance problem. So a distance problem involves using the original equation that distance is equal to rate times time. So what we want to do is manipulate this equation and solve for time. So if I want to get time by itself, I would have to divide by rate. So we end up with the fraction time equals distance over rate. And that's what we're going to use for our fractions for these problems. In the question, it should say in the same time. What that means is that the times are going to be equal. Since each fraction is equal to a time, we can set the two fractions equal to each other. Once it's set up as one fraction equals one fraction, we can then go ahead and cross multiply, or we can find an LCD for the two fractions and do what we've done up to this point. And then again, steps 4 and 5 are similar to the last one. Make sure you solve your equation accordingly, check your answer for extraneous solutions, make sure it makes sense in the context of the problem, make sure you're answering the question, and make sure you include your units. So let's look at an example. Manny rides his road bike 3 miles an hour faster than Veronica. If Manny travels 45 miles in the same time it takes Veronica to travel 36 miles, how fast is each of them riding? All right, so first we're going to set up our fractions. So Manny, remember we're using that time is equal to distance over rate. So Manny's time is going to be his distance, which is 45, over his rate. Now we know that his rate is 3 miles an hour faster than Veronica. So I'm going to call his rate x plus 3. So that means that Veronica, her fraction would be her time, which is equal to her distance, which is 36, over her rate. Well, if Manny's rate is x plus 3, that means Veronica's rate must be x. Now, there is another way to set this up. If you want Manny to be x, that means that Veronica must be x minus 3. Okay, we just know that Manny's 3 miles an hour faster than Veronica, which means that Veronica is 3 miles an hour slower than Manny. So we can set it up either way and we'll get the same final answers in the end. So now that we have our two fractions, it says that they're traveling in the same time. So that means that the times are equal. So Manny's time is just the fraction 45 over x plus 3. And Veronica's time is the fraction 36 over x. Now that I have one fraction equals one fraction, I'm just going to cross multiply. You can get an LCD and solve it the same way we did the previous problems, but this will just be a little bit faster. So 45x, and then this is 36 times x plus 3. So I'm going to distribute the 36. 45x equals 36x plus 108. And I'm going to subtract 36x. So I'm going to end up with 9x is equal to 108. And then I'm going to divide both sides by 9, so I get x is equal to 12. Now we want to make sure we're answering the question, how fast is each of them riding? So we solved for x, which was actually solving for Veronica's rate. So Veronica, her rate would be 12 miles per hour. Okay, from our denominators here, we know that x can't be 0 and x can't be negative 3. Which makes sense because we're solving for rate, so you wouldn't really have a rate of 0 or you wouldn't have a negative rate. And then for Manny, we're going to plug in the x, which is 12, into his rate. So 12 plus 3 is going to give us 15 miles per hour. Now, if you set it up a different way, like I mentioned before, if you made Manny x and Veronica x minus 3, when you cross multiply, the x you would get would be 15, which would be the x for Manny. And then when you plug it into Veronica, x minus 3, we would end up getting 12. All right, and the last type of problem we're going to look at is a distance with the wind or the current. So again, we're going to set up each person or thing as its own fraction, still using time equals distance over rate. Okay, the question should give information about a total time and a direction. So one way you're traveling with the wind or the current, which is making you speed up. One way you're going against the wind or the current, so that's going to make you slow down. Each fraction represents time in one direction. So if they give you a total time, we'd add the two fractions together and set it equal to the total time. Sometimes it might say in the same time, like the previous problem, in which case we'll set the fractions equal to each other and cross multiply. And then again, 4 and 5 are the same steps. Make sure you solve the equation accordingly. Double check your answer for extraneous solutions. Make sure it makes sense in the context of the problem. Make sure you're answering the question being asked, and also make sure you're including your units. So here's our example. You ride your bike to a store 4 miles away to pick up things for dinner. When there is no wind, you ride at 10 miles per hour. On your way to the store, you are riding with the wind, which is increasing the bike speed, but on the way back, you were against the wind, decreasing the bike speed. Today, your trip to the store and back took 1 hour. What was the speed of the wind? All right, so what we're going to do here again is set up each way as its own fraction. So we're going to say the first way is going to the store. Okay, so if we're going to the store, the time it takes to go to the store, and we're going to call that T1, so the time one way, is equal to the distance to the store, which is 4 miles, over the rate to the store. Well, without the wind, you're riding at 10 miles an hour. So we're going to have 10. But on the way to the store, you're riding with the wind that increases the bike's speed. So we don't know what the speed of the wind is, but we know that it's going to add to our distance or add to our rate to make us go faster. So we're going to have 10 plus x, and x would be the speed of the wind. So on our way back from the store, we'll say that T2, right, the time in the second direction, the distance from the store to your house is still 4, so your distance never changes. If you're going to somewhere and then coming back, that distance will always be the same. And now when you come back, you're going against the wind, which is decreasing the bike speed. So you're going to have 10 minus x. So you always want to make sure that your rate is always going to be first when you're writing the rate equation in the bottom here, this rate expression. And then the speed of the wind or the speed of the current will always be second. Okay, so it's going to be your speed plus or minus the wind's or current's speed. All right, we know that the trip to the store and back took 1 hour. So T1, the time one way, plus T2, the time the other way, has to equal a total of 1 hour. So the fraction for T1 is 4 over 10 plus x. So t1 plus the fraction for t2, which is 4 over 10 minus x, is equal to the total time, which is 1. Now this problem is a little bit harder than the previous ones because the denominators are not just numbers that are one term. Now we have two terms, but that's okay. Okay, so we're looking at three denominators, 10 plus x, 10 minus x, and this one has a denominator of 1. So if we're looking at all three, the common denominator here would have to be 10 plus x and 10 minus x. Now it looks like it's not so great, but what's actually good about this is that things will kind of cancel out. So if I multiply 10 plus x and 10 minus x to the first fraction, remember it's getting multiplied to the numerator only, so in the denominator the 10 plus x's will cancel out. So we're left with a 4 and a 10 minus x. In the second fraction, 10 minus x will cancel, so we're left with a 4 and a 10 plus x. And then this one doesn't have a denominator that we can cancel anything with, so we're going to have to multiply by both. Now, since they're pretty much the same thing, where one's a plus x and one's a minus x, if we FOIL this out, the x term will cancel out, right? So 10 times 10 will give us 100. 10 times negative x, we get negative 10x, and then positive 10x, they cancel. X times negative x is negative x squared. Okay, so we want to distribute the left-hand side. And even though this again looks bad, the good thing is that things will kind of cancel here. So 4 times 10 is 40. 4 times negative x is negative 4x. 4 times 10 is again 40. 4 times x is positive 4x equals 100 minus x squared. Now, these x terms should be the same, but opposite signs, so they should cancel out. We have a negative 4x and a positive 4x, so those are gone. The two numbers that are on the left-hand side should be the same. So 40 and 40, we're just going to add that to get 80, or you can do 40 times 2, whatever. And then that's equal to 100 minus x squared. Okay, so we're going to, even though we have a quadratic here, we don't necessarily need to set it to 0. We only want to set it to 0 if there's an x squared and an x. If there's only an x squared, we can get x squared by itself and then take the square root, which is what we'll do here. So I'm going to subtract 100, so I get negative 20 is equal to negative x squared. I'm going to divide by negative 1, so 20 equals x squared. And then I'm going to take the square root. Now when I take the square root of something, I know that I get two answers, plus or minus. And the square root of 20, because this is a word problem, we don't need to break it down with radicals. We can just plug it in the calculator and use decimals. So this would be 4.47. Now a couple things. The LCD here, if we set it to 0, our x's can't be 10 or negative 10. So negative 10 makes sense that it can't be. So it can't be 10. Our answer here is not 10, so that's fine. Because we have two answers that are plus, one's plus and one's minus, what makes sense in the context of the problem, this is the speed of the wind. You can't have a negative speed. So our answer for x is just going to be a positive 4.47, and this is going to be miles per hour. Okay, and then the last problem, Mexican free-tailed bats have an average flight speed of 25 miles per hour without any wind. Suppose it takes one of the bats 5 hours to fly 121.8 miles round trip. Assuming that the bat flew a constant speed, find the speed of the wind. So here they're telling us that it takes one of the bats 5 hours to fly 121.8 miles round trip. Well, if it's 121.8 round trip, that consists of the way there and the way back. So that means that 60.9 miles would be the distance each way. So we have, I'm just going to call this way 1. So the time it takes, T1, is equal to the bat's distance, which is going to be 60.9 because it's half of that round trip, over the rate. And now we don't know which way the wind is going. So if the bat's flying, which way is the wind helping, which way is the wind hurting? Okay, it doesn't matter because one way it's going to help and one way it's going to hurt. So we're going to say 25 is the speed of the bat without the wind. And I'll just say this is the way with the wind. So we'll say plus x. And then way 2, we're going to have T2 is equal to, again, 60.9 because that's the distance one way, and we'll say 25 minus x. And we know that it took the bat 5 hours to do this round trip, so T1 plus T2 is equal to 5. So just like before, we're going to set up our equation. So T1 is 60.9 over 25 plus x, plus T2, which is 60.9 over 25 minus x, and that's equal to the total time of 5. Our LCD here is going to be 25 plus x and 25 minus x. Sorry, that's a little hard to read. We're going to multiply that LCD to the first fraction, so we're going to have 60.9 times 25 minus x. We're going to multiply that LCD to the second fraction, so we're going to have 60.9 times 25 plus x, right, because the 25 minus x will cancel. And then here, we're going to have 5 times, and we're going to have to FOIL this together. So this is going to be 625, because that's 25 times 25. The x's will cancel, and then we have negative x squared. Okay, so this looks, again, not great, but let's go ahead and distribute. And we're also going to distribute that 5. So here, we have 1,522.5, which is 60.9 times 25, minus 60.9x, plus another one of those 1,522.5. So remember, the numbers should be the same. And here we have plus 60.9x. And again, these should be the same, and they'll cancel out those x terms. And then if I distribute the 5, this is going to give me 3,125 minus 5x squared. So here, the 60.9 x's are going to cancel out. 1,522.5 basically times 2 is going to give us 3,045. And that's going to be equal to 3,125 minus 5x squared. And now I'm just going to solve for x. So I'm going to subtract 3,125 on both sides. So I'm going to end up here with a negative 80 is equal to negative 5x squared. Divide both sides by negative 5. So I get x squared is equal to 16. And now I'm going to take the square root. So just like before, we get two answers, plus or minus 4, because the square root of 16 is 4. We know that x cannot be 25 or negative 25 based off of our LCD. Because this is the speed of the wind, we can't have a negative. So then our answer would be x equals positive 4. And then this is in miles per hour.